Good morning, everybody. My name is David Dugagne. I'm with ITASCA Minneapolis, a senior engineer responsible for technical marketing. Happy 3DEC Day. It's the 3rd of December, and we wanted to celebrate 3DEC. Today we have Dr. Jim Hazzard, a principal engineer with ITASCA Minneapolis, presenting. And he is a geological engineer with a PhD in geophysics. He has extensive experience in software development for geomechanics. He is currently the software manager at ITASCA Consulting Group, as well as the product manager for 3DEC. Dr. Hazzard is also a consultant with ITASCA and has worked on several projects evaluating the stability of open pit and underground mines. Other interests include numerical modeling of seismicity and hydraulic fractures. Dr. Hazzard is a registered professional engineer in Ontario, Canada. So thank you, Jim, and please.
All right, thanks, Dave. Here we go. This is a presentation about 3DEC. This is kind of a special webinar for us. It's not necessarily about things that are new in 3DEC. It's just more of an overview, although there will be some discussion about new features at the end. So the outline looks like this. What is 3DEC? And then just a brief overview of how you actually use 3DEC. Some of the main features, some applications that people do with 3DEC. And then I have a section about what's new. And if there's time at the end, I've even got a few slides that are like tips and tricks for advanced users. So we'll see how it goes. Okay, so if you're brand new to 3DEC, what it is a way to model assemblies of blocks, essentially. What makes it unique is you have these blocks that can interact at contacts. They can move past each other. They can separate. They can form new contacts. At the same time, the blocks themselves can be deformable, and the blocks themselves can actually fail like a small continuum model. So the range of applications that you can do with 3DEC is quite broad. So what I'm showing on this slide here is you can see the left is maybe something that's more like a continuum with a bunch of joints in it. You move towards the middle, you've got something that's more like a blocky system. And then you move towards the right, and it's something that's a true discontinuum with a large strain problem and pieces moving relative to each other. So we can cover this whole range of behaviors with 3DEC. And so even though it's got distinct element in the title, I think the acronym is 3D distinct element code or something like that. But really, I prefer to call it a hybrid method because it uses distinct element method to work out the contact behavior between the blocks. But the blocks themselves can be like continuum models. So it's really kind of a hybrid between a continuum and a discontinuum. And then the last bullet point here is as with all of the ITASCA software, it uses an explicit solution scheme. And what this means is that the solution marches through time, and so that information propagates through the system. So rather than doing a great big matrix inversion to get to some final answer, you have a sort of a gradual approach to get to the answer. This is a very useful and effective approach when you have highly nonlinear systems, which we almost always have in these type of discontinuum models. It's also a good approach when you have large strain. Again, things are moving and you need to update coordinates and so on. This approach is better and easier when you have large strain. And it's also a good approach when you have dynamic problems. Okay, so that was the 5-second overview of what 3DEC is. And here's the 5-minute overview of how you go about using 3DEC. So the way traditionally it works is that you build a model by starting with a block, or maybe more than one block. There are built-in commands that allow you to build different shapes. In this particular case, you can see I started with a many-sided cylinder, but often you just start with a block or something else. And then what is unique about 3DEC is that you have the ability to cut that into pieces. And so this cutting is used to either create different geometries, like cutting out a tunnel or something like that, or to put in actual joints and faults where you expect to see movement. So the cutting logic is pretty sophisticated. You can just cut planes, so you give like an orientation and origin, and then even perhaps a spacing or some random distribution of orientations and spacings. So you can cut out joint sets that are just planar. You can cut out any sort of 2D shape and extrude it. So if you had some sort of tunnel or something like that, you can cut that out. As of version 7, I think you can cut imported geometries. And by that, I mean like a DXF or some sort of triangulated surface. So for example, if you had a fault plane that was defined by a DXF, you could import that and just cut right through your model to create that fault plane. The top right picture here is actually showing that. This is a non-circular, it's kind of a weirdly elliptical tunnel here that was imported as a DXF, and then it was used to cut through the model. And then the last bullet point here is you can generate discrete fracture networks. This is a capability that exists in all of the ITASCA programs, the ability to create a fracture network with different size distributions and orientation distributions and so on. But what's unique about 3DEC is that once you have the discrete fracture network, you can cut it. You can use that to create a model with a bunch of joints in it that match the fractures that you just created. So, and that is showing on the left-hand side the DFN that was created, and on the right-hand side, the 3DEC model that results from cutting. Okay, so that's the traditional way to build a model, is to start with a big block and cut it into pieces. More recently, there have been other ways to build these models. In this example, I'm showing how you can, again, import a geometry. And by geometry, I mean a triangulated surface like a DXF. As long as it's a closed, watertight geometry, you can then just have 3DEC create a model by filling it with tetrahedral blocks or actually filling it with tetrahedral zones. So you can see this plot here, that the front of this one is cut away so you can see inside of it. But you can imagine there's actually another plane here so that it's a closed volume. And then I just say, okay, fill that up with blocks, or in this particular case, I'm showing fill this up with zones. And it still respects the joints and the boundaries and things like that, right? Similar idea here, you might, instead of filling it up with blocks and joining them together or filling it up with zones, you might want to fill a shape up with blocks and not join them together. So for example, on the left-hand side here, maybe you're doing like a unconfined compression test, and you make a sample with a whole bunch of tetrahedra stuck together, and you squeeze it, and you can watch them sort of fracture and break apart and crack and so on. And this is a thing that people do with 3DEC. They don't have to be tetrahedra. We also have the ability to generate Voronoi, which I'm showing here on the right-hand side. And then you can take this to another level. So imagine you have a shape and you fill it up with tetrahedra, like I'm showing on the left-hand side here. You can then cut a sort of a second layer of joints on top of that, right? So you have your sort of background joints in between all the tetrahedra, and then you have the more large-scale joints cut through that. So in this particular case, these were sort of wavy, I think they were probably veins, and we were able to cut these sort of wavy shapes into this tetrahedral model, and you end up with a result like you can see on the right-hand side here, where you have all these little tetrahedra that are potentially cracking and falling apart, but then you also have movement on these larger scale joints. As you can see, the sort of stress discontinuity there across some of these wavy joints. So you kind of have this like two layers of discontinuities going on in these models. Another thing that people often do is what we call here an octree model. And so again, you would start with importing some sort of geometric surface, and then what you do is you densify the blocks close to the surface, and then you sort of do this iteratively. So you have smaller and smaller blocks close to the surface, and then bigger blocks away from the surface. And this allows you to create a model that sort of matches the surface. I mean, it's not going to be a perfect match because it's going to be this sort of sugar cube geometry. But certainly for things like open pit mines, it's probably close enough, and it allows you to very easily match this this surface, and then delete the zones that you don't want or delete the blocks that you don't want, and do these sort of open pit type models. And then lastly, of course, you can import from Griddle. Griddle is another program that we sell that just does meshing. It doesn't have to be Griddle. I mean, we have file formats for importing meshes into 3DEC. If you have another program that's capable of doing that, you could generate a mesh and import it into 3DEC. But be aware that 3DEC is a little bit weird compared to a continuum program because we have these joints in here. So Griddle is specifically set up to allow you to create a model that looks like this, which is sort of mostly continuum with a bunch of joints in it. And it works pretty well. Okay, so everything up till now, I've just talked about how to actually build the geometry of the model. Once you have the blocks created, then you decide whether or not you want to zone them. And so what this means is that I could, on the one hand, just leave the blocks as rigid. And by rigid, I mean the blocks themselves do not deform. All of the action occurs at the contacts between the blocks, okay? This is useful in problems like, for example, masonry, where you have maybe strong, stiff blocks that are joined together with weak joints, so all the action is happening on the joints. In the geological world, more often we have movement on the joints, but we also have deformation of the volume itself, and potentially even failure of the volume itself. So I would say most of the time in these geotechnical type applications, you create your blocks and then you fill them up with zones. And so what you end up with is like a little continuum model inside of each block, which is just a zoned, a zoned volume. And once you have the zones, then you can assign whatever constitutive model you like, right? So again, it's just like a continuum model. So I'm showing here on the left side a Hook Brown failure envelope. You could make this material Hook Brown material. You could make it more Coulomb material. You can make it whatever you want. Pretty much all of the constitutive models that are available in FLAC 3D are also available in 3DEC. So you can have movement on the joints, but you can also have deformation and failure and shear bands forming and cool stuff like that happening in the zones as well. Okay, so you figure out what your joint properties are. You give it a constitutive model. You give it a Young's modulus and Poisson's ratio and all that stuff. Now you need to worry about the joints. Same problem, right? You need to decide on a constitutive model for the joints and then assign the properties. Probably 90% of the time, you will be using more Coulomb joint constitutive model. And that's the sort of sliding joints that everybody is comfortable with, where you give a cohesion and a friction and so on. But be aware there are other constitutive models available in 3DEC for the joints. So the left-hand plot here shows an actual creeping model where the shear stress is held constant, but the thing still moves with time because of a creeping mechanism. The right-hand plot here shows it's sort of a standard more Coulomb, but instead of an instantaneous drop in strength when it starts to slide, you have a more gradual drop in strength when it starts to slide. So it's more like a softening type of thing. And you can even set it up so that it heals when it stops sliding. So you can get this sort of stick slip behavior that people are interested in when they're doing seismology and things like that. Okay, so you build your model, you zone it or not, you assign your properties and your constitutive models, and now we need to get to the point where we're going to solve it. So you need boundary conditions, as with every numerical model. You may or may not need initial conditions. You can create histories, and what histories are essentially measurement points where you can monitor what's happening as the solution progresses, which again is another cool thing you can do with the explicit approach, because again, it sort of marches through time, so you can watch how things are moving or stresses are changing through time as you do the solving. And then you say solve or not. And what I mean here is that, a lot of the time you just want to get to some steady state, some equilibrium. everything has stopped moving, and you figure out what the stresses are and the displacements are. So maybe this top right plot here has reached a state where everything's in equilibrium and it's just sitting there. You can do that. You just say solve, and it tries to get to this state. Often this is not what you want to do, or often it will not ever reach an equilibrium state. So the bottom left plot here is showing, for example, a series of columns made up of blocks that are subjected to different earthquakes. And depending on the severity of the earthquake, these things may or may not fail. And of course, once they fail, they will not then reach an equilibrium state, right? Pieces are collapsing and they're falling. You're not going to get to that solid state. So you have the potential to say solve, but sometimes it doesn't solve. And that's intentional. And again, this is an advantage of the explicit approach, is you can look at the way that these things fail and the movement as they're failing and not necessarily get to that equilibrium state, which is different from the more traditional implicit approach where, you just say solve and it either converges or it doesn't converge. And that's it, right? You could say it converges or it doesn't converge. You can't necessarily look at the path on the way there. Okay, so you solve it or you don't solve it, whichever. Some calculation has been done. We have a bunch of fairly sophisticated post-processing capabilities within 3DEC. So of course you can make contour plots, you can make cut planes to look at 2D sections, you can make isosurfaces, which I'm showing here. You can paint data onto imported geometries. So this is what I'm showing in this plot here. Imagine you have a whole bunch of tunnels like this, and you don't actually want to create a numerical model of all these tunnels because that would be quite challenging and computationally intensive. However, you do want to see where the high stresses are, or maybe where the high displacements are, because you need to know, where you need extra reinforcement or something like that. So what you can do is you can solve your model and then import these geometries and paint information on top of them. So in this example, we're importing these tunnels and painting the strain on there. And you can see some of these areas are in red, where you might be expecting a lot of movement or deformation on these tunnels. And this is where you might want to worry about, your support systems. We can make movies, which is super useful in dynamic problems. There's all kinds of graphing of the histories and also of like profiles, if you want to look at surface deflection or something like that, along a line, you can do that kind of stuff. And there's, of course, high resolution export for reports and presentations and so on. Okay, so that's the basics of how to use it. I'll just talk a little bit more about some of the features I haven't mentioned yet, and then show some applications. So features. So one thing you can do in 3DEC is fluid flow, both in the joints and in the blocks themselves. And then there's actually communication between the pore pressures in the joints and the pore pressures in the blocks. So that's what's showing in this little movie here. You can imagine you've got pore pressure being applied to the left-hand side in the joint, and it starts to flow along the joint, but it also leaks off into the matrix. And depending on the permeability of the matrix, you can have more or less leak off, right? The other thing about this fluid flow is that it's fully coupled. Mechanical fluid coupling, meaning that if you change the pore pressures, it will cause deformation, right? So imagine the pore pressure increases in the joint, it will push the blocks apart. Similarly, if the blocks move, it changes the aperture of the joints, and that changes the rate at which the fluid flow. So there's this two-way coupling. The fluid affects the solid, and the solid affects the fluid. Now, traditionally, we have solved these things explicitly in the same way we did with the mechanical. That can potentially be quite slow in a fluid flow analysis. So in the latest version of 3DEC, in the 9.2, we've introduced an implicit calculation scheme, which is potentially way, way faster when you're solving these joint flow problems. Okay. Another thing that people often do is this factor of safety analysis. Probably you're familiar with the shear strength reduction method, where you sort of gradually reduce the shear strength of the material and see if it fails. This capability is built into 3DEC. I will automatically, run multiple tests for you with different shear strength reduction and work out the factor of safety. You can either get a global factor of safety, so the stability of the whole system, or you can do something like, as shown in this plot here, where you're looking at local factors of safety. Some parts may be failing at one level of shear strength reduction, some parts might be stable, and so on. So you can look at sort of a distribution of factors of safety rather than just a single number. Structural support. So what I mean by that is liners, shotcrete, bolts, cables, tiebacks, whatever you're using to support your soil or your rock. This has been in 3DEC for a long time, but some new things in version 9, we have the ability to have liners that can fail. So before version 9, you could put a liner in there and you give it a Young's modulus and a Poisson's ratio, but it was always elastic. Now you can actually give it like a cohesion and friction or some other things, and the liners themselves can fail, and you can see this more interesting deformation behavior in these failed liners. And then new in 9.3. 9.3 is not actually out yet, but in the next couple of weeks, we'll have a 9.3, which will add the ability to plot these bar charts on top of the one-dimensional elements, cables, bolts, beams, and so on, which is kind of cool. It's just a nice way to visualize results. I also should mention something that's useful in 3DEC is what we call hybrid bolts. And what this is basically just cables with an extra spring in them that resists movement on the joints. So because in 3DEC you're almost always modeling some sort of jointed material, the ability to have these cables resist the joint movement. So imagine, you have some sort of steel piece that's crossing a joint. You can imagine if that joint tried to shear, there would be some resistance there. You form like a little bit of a bend that resists that movement. So that is something that's built into 3DEC with these hybrid bolts, and people use that all the time for modeling jointed systems. Okay. And then of course, scripting, really this is probably the major strength of the ITASCA software is the ability to do this scripting. We have our own built-in language called Fish. There's also Python as of version 7, I think. The scripting is cool because it allows you to access every single variable in the model. So displacements, velocities, temperatures, stresses, whatever you want, you can access it with the scripting. Most of them you can change, not all of them. Some of them are read-only, but most of them you can change. And this allows you to do all kinds of interesting and complicated things like, parameter studies where you're changing different properties, changing the physics, right? So I've seen people do things like change the modulus of the material based on the temperature because it freezes and things like that. So almost anything you can think of, you can do with this scripting. So this is really where the power of using this software comes in. Okay, and then on top of the basic features, we also have options. These are traditionally things that you would pay extra for and buy an option. One of them is dynamics. Let's see, this is a movie, I think. Yeah, so you can look at things like wave propagation and reflections off the joints and the surfaces and things like that. This is useful if you're trying to simulate an earthquake or potentially a blasting type of scenario, something like that. There's also an option for thermal. So again, you can look at the propagation of heat through the system, given some sources and sinks. And then there's also the heat affects the mechanics. So, things will expand and it will cause things to move and so on. There's creep. I put this under the options page. It's not actually an option in 3DEC. It is an option in FLAC 3D. It's not an option in 3DEC. It's just included. And what creep is the ability for things to move or for things to deform with time. So there's some viscosity involved here. And something that used to be an option is what we call user-defined models. So I showed earlier how you have constitutive models for the zones, like Moore-Coulomb and Hook-Brown. You have constitutive models for the joints, like Moore-Coulomb or whatever. You also have the ability to write your own constitutive models if you really wanted to. And some people actually do that. So if you have an idea or a particular kind of physics that you want to simulate, you can write your own constitutive model. It creates a DLL. It just plugs in and works exactly like any of the built-in constitutive models. This used to be an option. Now it's free. So anybody can do this. And it also means you can use somebody else's constitutive model and plug it into your model. Actually, on our webpage is a page of constitutive models that other people have written. And if you're interested, you can go and look at that and use somebody else's model. So, okay. So that's the main features. And now that you know about the features, I can just zoom through some things that people actually do with 3DEC. A lot of these examples come from our own consultants. A lot of them come from other people. Some of them I've just taken from papers, from journals and things like that. So certainly a common one in our office is underground mining. The left plot is what you've seen before. In this particular study, they were looking at examining the effect of different support systems, so different lengths of bolts and different types of bolts and things like that. The right-hand plot here shows a more three-dimensional style underground mining situation, just looking at stability and so on. A unique thing about 3DEC is that you can look at these sort of fragmentation type problems. So again, if you build up a model with a whole bunch of tets stuck together or Voronoi or whatever shape you like, and then do an excavation or subject it to some other kind of load, you can see these things break apart and you can look at the fragmentation. And there's actually some built-in logic here that will calculate the fragments based on the contiguous pieces, and you can get statistics about, fragment volumes and things like that. So this kind of thing is something that people do. Open pit mining is also a very common use of 3DEC. Anybody who does open pit mining knows that often the big problems are a result of the joints and the faults, and the ability to put those in these models is beneficial. So here's just a couple of examples showing open pit mines that our own consultants have done. The previous plots here were showing mine scale. So this is more or less a whole pit, or maybe a quarter of the pit. If you wanted to get into more detail, you could look at a bench scale. So in this case, you can see this is just a single bench, I don't know, 40 feet high maybe. The faint gray lines are showing you all the joints that were cut into this thing. But what you can see is these formation of these individual wedges and the failure and collapse of certain pieces of the bench. So if that's the kind of thing you're interested in, you can do that kind of modeling too. Doesn't have to be mining. People use 3DEC in civil engineering. The top right plot here is some subway tunnels, I think in Sweden. A part of this model was filled up with joints just to see what happens there at these tunnel intersections. The bottom plot here is a power cavern related to hydroelectric energy generation. And again, the ability to put in all these joints and look at the behavior is valuable. Masonry, a lot of people are using 3DEC to look at masonry problems. Often masonry structures subjected to earthquakes. So you have a lot of these old churches or old mosques or old bridges in parts of the world where they get a lot of earthquakes. And so you can use a dynamic option, build up one of these things, subject it to an earthquake and see if it fails or what the deformation is and what kind of support you might need. Hydraulic fracturing, because we have the ability to do fluid flow in the joints, you can do these sort of hydraulic fracturing problems. This particular example here is actually a geothermal problem where they were injecting fluid into a fractured I won't say reservoir, it was more like a igneous type rock, but to try and sort of stimulate regions of this geothermal reservoir. And they also wanted to see whether or not it was going to cause movement on large scale existing faults. So the gray planes on here were like large scale faults, and they were worried about the fact that, this injection might actually cause movement on the big faults, and that's what they call induced seismicity, and that's what they're worried about. Nuclear waste disposal, because we have the ability to consider thermal effects, plus hydraulic, plus mechanical, then you can start to do some complicated things that people do in nuclear waste disposal problems, and look at the stability of these things. Dams, people use 3DEC to look at dams. Again, the ability to put a dam on top of a fractured base and potentially have fluid flow through and around the dam is interesting. Landslides, this is a movie. Again, you can run these things in large strain, and all the pieces can break apart and form new contacts and so on and so on. So you can look at these large strain type problems and consider things like run out and stuff like that. There are other crazy things that people do with 3DEC. This is another example from our own office. This is an ancient Native American sort of settlement in Colorado. Obviously nobody lives there now, but it's sort of a historical artifact, and it's protected by this overhang. And they're very concerned about the fact that this overhang might collapse or partially collapse on top of this these dwellings below. So we use 3DEC to look at, how stable it is and what kind of support might be required to hold it up. So you can do fun stuff like this too. Okay. So there are other applications, but that's sort of some of the highlights. I'll just spend a little bit of time talking about what's new, starting from version 9. So you can, for those that don't know, you can buy version 9 perpetual license and own it forever. But we've also started moving towards more of a subscription style of sales model. And the point here is to be able to give people new features faster. So instead of releasing a version 9 and then 3 years later releasing a version 10, there is a 9.1, a 9.2, a 9.3, and each one of those sub releases there'll be new features that people can use, and you can get those sub versions by having a subscription. So most of what I'm talking about is just new in 9, but some things have been added to these point releases. So version 9, the look and feel is a little bit different than previous versions. You can see here the color schemes are different. The icons are different. One change is that, we used to have the plots as tabs. And what would happen is that people would make, dozens or maybe hundreds of plots, and it was impossible to find them because you've just got all these tiny tabs at the bottom. So instead, this idea of the plots has been moved over here to the left-hand side. The main screen here, you've got this main screen area here. You can split it, so you can show a data file and a plot or 2 plots, and you can keep splitting it, so you can have 4 plots or 8 plots or whatever. And then if you want more real estate here, you want to show and hide different things, there's some buttons down at the bottom that make it super easy to just turn on and off the different components. For those that are way behind in their 3DEC, you can see over here on the right-hand side, this fish global symbols. This has been in here since, I think, version 7. But it's pretty cool because you can have a model running, and it can show you over here on the right side what the fish variables are as it's running, which is sometimes useful. The inline help has been improved in version 9. So this was available in version 7, where you start typing a command and you hit Control Space, and it shows you what possible keywords you can have. So for example, in this example, I started typing block create. I hit Control Space, and it tells me, okay, I can create a brick or a drum or a polyhedron. What's new in version 9 is that instead of just showing you the keywords that go with what you typed, it shows you all the possible commands. So I can scroll up and down in this window and see all the possible commands that I could use. Also, this window is now sticky, so you can just leave it sitting there and keep on doing your typing and then look at what commands are available. And also you can just click on one of these commands and hit F1 and it takes you to that section of the manual, which is super useful. Other UI improvements, I mean, these are relatively minor things, but they can sometimes be super useful in your day-to-day work. The ability to create a your own contour ramp. So a lot of people have asked for that. They don't like the red to blue or, you know, green to other green that we provide. So you can just basically create your own. The ability to change the legends. So in previous versions, the legends are always showing scientific notation. Sometimes that's annoying if, you know, you have decimal examples like this, so you can just change it to be decimal and you can specify the number of decimal places, and it's quite nice. You now have the option to omit past states when plotting yield. So in the past, you would say, show me everything that's yielded, show me the states, and you get tension now, tension past, shear now, shear past. Often you don't care about the past, so you can just click a button and that goes away. Some other cool things for the plotting of the charts and the graphs, you can switch the axes around, you can make logarithmic axes, you can add minor grid lines, you know, stuff like that. A big thing in 3DEC specifically is that most of the plot items have been multi-threaded in version 9, meaning that when you create a plot of blocks or joints, it will go significantly faster than it used to. Performance improvements in version 9 and above. Solving to steady state up to 10 times faster. So we made some changes to the way that the time steps are calculated and the damping works and some of the other underlying physics here. And what it means is that, you know, the individual time steps aren't necessarily faster, but getting to steady state is significantly faster. And in the same way as getting to steady state is faster, running a dynamic analysis is also faster. So even if you're not getting to a steady state, the dynamic time steps are larger, and this allows you to do your dynamic analysis more quickly. The save and restore is also a lot faster, and as I already mentioned, the plotting is a lot faster. Well, this is just an example of what I was talking about. So this is an example from the manual. It's a tunnel in a fractured rock. To get to the initial steady state in version 7 took almost 28,000 steps, and in version 9 it took about 2,800 steps. So it's almost 10 times faster to get to that steady state in version 9. Similarly for dynamics, you know, you've got some sort of jointed material like this. You end up with a relatively small time step. The time step depends on the size of the zones. So when you have these joints very close together, you end up with a relatively small time step. But in version 9, again, these time steps can be up to 3 times bigger than they were in version 7, which is useful. Also, I mentioned in version 9, we have these nonlinear structural elements. So this is just a super simple example of a plate being pushed up from the middle. And in the past, this would just behave elastically. So you can see the curve, the applied pressure versus the deflection is just a linear line. But now these things can fail and go plastic. And so what happens is this thing fails. It can no longer, the load can no longer increase, and it just keeps on deforming. And so you can model these types of things now in version 9. There's some new constitutive models. One is columnar basalt. So this was actually developed as part of a project related to looking at dams in China, where they often have these columnar basalts, and how you would go about modeling these things. It's more or less the ubiquitous joint model, but you can specify 4 different joint sets. And so in this way, you can have 4 different joint sets, and you can model these types of systems. In 9.2, so fairly recent, we've introduced the piecewise linear Mohr-Coulomb. So you can have a curved Mohr-Coulomb envelope And you can either define that with an equation or with a table, and just giving these different pieces like I'm showing in this plot on the bottom left. There's also a concrete model. And I think I've got this on the slide. So this is an example. You've got a concrete beam with some like steel reinforcements in it, and you're doing like a point loading type of thing on it. You can see how it bends. You can see that the behavior is sort of nonlinear. And what's interesting about the concrete model is it's got this damage parameter, so you can actually look at the damage in this model. Another new thing in version 9 is coupling with FLAC3D. So imagine this is an example here where you've got a bunch of 3-deck blocks. So these are a bunch of tetrahedra stuck together. And outside of that, you've got FLAC3D zones. And these things are coupled together. And you can see that the coupling works pretty well. This is a contour of displacement that results from doing an excavation. You can see how the contours are pretty continuous across the boundary between the 3-deck and the FLAC3D. It also works dynamically. So imagine we apply a pulse to the surface of that excavation, and the wave will just propagate right from 3-deck part into the FLAC3D part, and it works pretty well. New in all of the ITASCA software in version 9 and above is this AI assistant. And so what this is it's an AI type of, language model type of thing that's only been trained on our documentation. So it's not taking information from the entire internet, like say ChatGPT. It's only taking information from our documentation and allows you to ask questions related to using the software and get answers in plain English or whatever language you like. So this just shows an example here. You type in a question in plain English, it gives you an answer. It often gives you an example of commands or fish, and it almost always gives you a link back to the documentation to get more information. This is useful because as we all know, the AI is not 100% correct and can sometimes hallucinate, but it will give you pretty close to the right answer. I've tried it quite a lot and it works pretty well. And again, it gives you the links back to the documentation if you want to go and double check things. You can get there from the help menu. You just go to help, ITASCA AI assistant, and then you can get there. Some other new features, Timoshenko beams, log normal distribution for DFN fracture sizes. A few people asking for that. Integration with RockMass. So RockMass is a company that builds hardware for scanning and measuring discontinuities and surfaces of rock, often related to mining. So we have a bit of a partnership with them so that we can read in their file formats. So if you use their tools to do some scanning and you get a bunch of discontinuities that you've measured, you can then import that into 3-deck and then create joints out of it or whatever you want. And then, as always, there are some new examples. Okay, I think that's pretty much it. There are other new features. I'm not going to talk about all of them, but this is a very high-level summary of the history of 3-deck. Basically, so in 3-deck 4.1 is when we introduced the GUI. So that was 2007. Before that, if anybody's old enough, they'll remember that it used to be this console-only type of version. So that was a big deal, introducing the GUI in 2007. Version 5 introduced multi-threading, so that was a significant improvement. 3-deck 5.2, a few years later, was further performance improvements, so things went quite a bit faster in 5.2. Version 7 was a big change. We introduced new command and fish syntax. This was necessary for several reasons. Number one, in order to do the coupling between the different programs. Number two, to do the inline help that I was showing you about, that control space. Number three, to do multi-threaded fish, which is potentially really useful if you're running a lot of fish. The multi-threaded goes a lot faster. Version 7 also introduced Python, the model building from geometries that I showed earlier, the Voronoi, and the hybrid bolts. Version 9 was the updated UI that I showed earlier, multi-threaded plotting, the faster solving to steady state, faster save and restore, the plastic structural elements, coupling with FLAG 3D. Since then, there's been a 9.1 and a 9.2. There's been, minor improvements in those, but the big one in 9.2 is the implicit fluid flow, which can potentially make the fluid flow go a lot faster. And that's basically the end. Here's some links. We'll send out these slides afterwards. Dave, is that correct?
Yes, that is correct.
So
send out a link.
So these are links that you can just click on and get to stuff. Some useful things here. So the 3DEC main page, the Software Academy is basically training courses that you can look at. The YouTube channel, we're actually trying to move a lot of our training material onto YouTube. It's easier to find and people like it. The software forum is just a traditional kind of forum where people ask questions and other people answer them. There's a lot of information there. It's all searchable. It's quite good. And then get a 3DEC quote. So I think I'm done.
Okay, great. Thank you, Jim. So we've got quite a few questions through the Q&A. So again, if you do have a question, click on the Q&A icon at the top of the Teams app, and we will try to answer them. So we have quite a few. Let me start with the first one. In this version, version 9, is it also like version 7, heavily dependent on geometry that softwares, and we have no geometrical features inside the deck, the mesh building?
Yeah, somewhat. I mean, as mentioned, you can import a geometric surface as long as it's closed and airtight, and then build the model from that. But yes, the challenge is to build that airtight closed surface, and most of the time you'll probably need Rhino or some other type of CAD program just to build that surface. And then once you have that, you can bring it into 3DEC and build the model. So
yeah, and then of course with 3DEC, you start with blocks, and you could always cut smaller blocks from that.
Yeah, and we've tried to make it possible to, maybe it's quite painful to make this closed, airtight, perfect surface in Rhino, but you can make a less perfect surface and use that for cutting. So if you have a weird shaped tunnel, you can import that and then cut it out of your block. That's possible too.
Okay, there were a couple of comments off that question. So default zones are always tetrahedral?
Yes, because the geometries that people create in 3DEC are often quite weird. We give you the ability to do this cutting, which means that you can end up with very complicated, ugly geometries. Filling those up with hexahedra is quite challenging. And so filling them up with tetrahedra is relatively easy. So it's almost always tetrahedra. And the other reason there is that we assume that if you're using 3DEC, that you're mostly interested in the movement on the joints and discontinuities. You can still have, of course, deformation and failure in the blocks themselves. We all know that the tetrahedra are less accurate than the hexahedra, but we're making an assumption here that maybe you don't care about super duper accuracy of the deformation of the blocks because most of the action is happening on the joints. So, I mean, that's just life. I mean, with these complicated geometries, we can fill them up with tets. It's much harder to fill them up with hexes. So that's what we do.
How can we address the issue of crack generation in a complex model, especially when the approach in 3DEC does not consider crack formation in the same way as PFC?
I mean, you could theoretically run 3DEC in the same way that you would run a PFC model, is that you fill up a volume with a whole bunch of blocks and stick them together and apply some sort of boundary conditions and watch it crack. That's not really the most efficient path with 3DEC. You can do it with 3DEC. It will go faster in PFC because PFC is designed to do that kind of stuff. But you definitely can do that in 3DEC. And I showed some of those models with, 10,000 or 100,000 tets stuck together. You can give them some strength at the boundaries and apply a load and watch them crack and the cracks propagate along through the tets. I mean, you can definitely do that kind of stuff in 3DEC.
Is Barton-Bandis joint model built in?
It is not. There is no three-dimensional version of the Barton-Bandis joint model. Not that we didn't include it. It just doesn't exist in the world. So if some researcher comes up with a three-dimensional version of the Barton-Bandis model, then we will include it. But so far, that doesn't exist.
And then the last comment on that question, the original question, just a statement. Another application of 3DEC could be simulating block flexural toppling failure, which continuous models are unable to handle.
Yeah, for sure. And there's another cool thing I didn't show in here, but somewhat related to that is you have the ability to look at deformation modes. So people who are doing these masonry problems will often want to know the different modes of deformation. And so you can do that. It involves, sort of a matrix inversion, but that's all built in. And so you can look at the first 6 modes of deformation or whatever, this kind of stuff with these masonry models. It's kind of cool.
I can answer this one. Do you also offer free trial licenses? Yes, we do. And at the very end, I'll put up a slide with an email that you can contact us at to request a 2-week free trial of 3DEC or any of our other software. So I'll show that slide at the end. Can 3DEC create gradual increased sizes of Voronoi based on the geometry, like Octree?
That's a good question. I'm not 100% sure about the answer to that. I don't actually know. I'm not sure. I have to get back to you on that.
Yeah, it would be a much more complicated geometry than.
Well, I mean, you have some control over the sizing of the Voronoi. So there are some keywords that say, minimum size, maximum size, but I'm not 100% sure how the gradation works. I don't know. I'd have to look that up and make a note.
Is it possible to show the contact state as a line rather than symbols like diamonds in 3DEC, just like UDEC?
Yeah, that's not built in right now. What people often do is they write a little fish that assigns a group name to the contacts based on how many subcontacts fail. The problem is, the difference is that in 3DEC, because it's three-dimensional, you have a contact, imagine it's a triangular face, and then there are 3 subcontacts associated with that at the corners. And so, one of those subcontacts might have failed and 2 of them might not have failed. So is that contact failed or not failed? It's sort of undefined. So traditionally what people do is write a little fish function that says, if any of the subcontacts have failed, I'll give that contact a group name and call it failed, and then I can just plot it as lines. Or if all 3 of the subcontacts have failed, I'll call that contact failed, and I can plot it as lines. So to some extent, it's a little bit up to the user to decide what constitutes a failed contact. Having said that, that's probably something we could build in. I just haven't done it. It's actually a good idea, so I'll write that down too.
Will 3DEC 9 speed up the calculation process? Is there any command or config that might help?
Yeah, like I said, the time required to execute an individual step in version 9 is not necessarily faster. It's faster to get to a steady state, or it's faster to get to whatever state you're trying to get to, because essentially the time steps are bigger, is what it boils down to. So, you will get to your answer faster, but the individual time steps are not necessarily faster, if that makes sense.
Do you mean there's the same number of time steps? They're just bigger steps?
Right.
Okay.
Basically, yeah.
And okay. Has the workflow to excavate a bench on a pit slope changed between version 7 and version 9?
I wouldn't say so. No, I mean, as far as I know, you just identify the blocks that need to be excavated at different stages and then just delete them and then, carry on. Or actually what has been added in version 9, what's new in version 9, which I didn't mention, was a relax type of command. And so what that does is instead of just saying delete, and then everything is instantaneously deleted and you get potentially like a big rebound, you have the ability to do it more gradually. And so I think the command is block relax. And so what it does instead of just deleting it instantaneously, it sort of gradually deletes it so that you don't get this like huge rebound instantaneously. It's sort of simulating a more gradual excavation. So actually that's a new thing in 9 that I forgot to mention, the block relax, which is useful.
Yeah, that's great for any excavation, tunnels, pits, stopes. Someone's asking if we can show them where they can find detailed descriptions of different constitutional models. So I will reply to you directly, and I'll send you a link. We have a set of online documentation. It's docs.itascacg.com. And all our version 9 software documentation is available there. It's the same documentation that's built into the software, but I will send you a direct link. There's a question: in order to test 3DAC, how many blocks does the demo version allow? So we have two options for testing the software. There is the demo. For 3DAC, it is limited to 50 blocks and up to 1,000 zones. And then there's some other restrictions, but it doesn't expire, it doesn't time out. And then shortly, I will put up a slide with an email that you can contact to request a free 2-week trial. And then that's fully functional, includes all the options. So it's probably a better option for you is to try the trial, because then there are no limitations. Question: how can I perform strain burst and shakedown rock burst event modeling?
I don't know. That's a big question. I mean, if I was doing strain burst, I would use dynamics. Well, maybe. I mean, it depends what you're trying to get out of it. You would have some sort of stressed up system, a bunch of blocks with a bunch of joints that are under high stress, and then you would have to perturb it somehow to see that thing burst. So, maybe weaken the joints slightly or apply a small load or excavation or something to see if that thing bursts. And the instability of the burst will depend on, to some extent, the constitutive model that you're using. So if it's a rapid stress drop, then you might see something catastrophic. If it's something more ductile, then it might not burst in the way that you're expecting. So I don't know, it's kind of hard to answer right here. I mean, it's kind of a complicated problem. So
yeah, I have seen projects that our consultants have done where they've used, I'm not sure if it was 3DAC or UDAC, and they essentially were looking at pillars and bursting in pillars in high stress situations. So it is possible. Is there any way to introduce more realistic waves rather than sine and cosine for dynamics?
Yeah, I mean, you can introduce whatever you want. Most people who are doing this in reality for like earthquake studies will have a table of velocities versus time, or accelerations versus time, or even displacements versus time. So you can just apply that table to get a realistic earthquake. There's a whole other body of knowledge related to simulating these earthquakes. You probably want to do filtering and stuff like that. But yeah, you can apply whatever you want. Usually people do it with a table. You could write your own fish function to do something else, but mostly it's with a table. So yeah.
And we do have a seismic wizard in 3DAC.
Yeah.
Pre-processing signals.
Right.
Okay. thank you for your presentation. You showcased several examples that inevitably involved rigid blocks. When modeling at the mineral scale using rigid blocks, what are the main differences between FLAC 3D, PFC 3D, and 3DEC? Under what circumstances would you choose one software over the others?
Yeah, that's a good question. To be honest, if I was modeling rigid blocks, especially at a grain scale, I would use PFC because that's really what it was designed for. In PFC, the blocks are always rigid. There are certain efficiencies by assuming that the blocks are always rigid. So if you run the same model in 3DEC and PFC, it'll go faster in PFC. That's the bottom line. You can do this stuff in 3DEC. If you want to, if you own 3DEC and you want to do it, then go ahead. But if you're trying to decide what you wanted to buy to do those sorts of problems, I would choose PFC, to be honest. So
yeah, and remember that PFC is no longer limited just spherical or circular particles. You can have polyhedral, polygon shaped objects. So you have an image, a slice of a rock sample. You can actually recreate that pretty precisely. In general, when people ask sort of the difference between the three in a general sense, a lot of it has to do with the number of joints. So, FLAC 3D, dozens of joints, 3DEC, thousands of joints, PFC, tens of thousands or hundreds of thousands of joints. It's sort of the scale that we look at. Will 3DEC 9 speed up servo-controlled tests like loading controlled by fish?
Probably. I mean, again, you'll get to your answer faster. So I expect so. I haven't tried that specifically, but probably.
And I'll just add, if you're doing that sort of developing those sorts of fish functions to access the model, read something, perhaps change something, like the velocity of the platens. If you're not using multi-threaded fish, then you're really losing out on a lot of performance improvements. So with multi-threaded fish, with splitting, with lists, with operators, there's a whole host of orders of magnitude improvements that you can reach with multi-threaded fish. It is a little bit different from conventional fish, but we have quite a few examples and documentation to help you learn that. But I would expect if you're not using that, you'll see a tremendous improvement in that sort of thing, especially when you're essentially calling on a fish function while you're cycling. Okay, a few more questions. How can we address the issue of crack generation in a complex model, especially when the approach in 3DEC does not consider crack formation in the same way as PFC?
I think we had that one.
Oh, I'm sorry. You're right. I went the wrong way. Will a perpetual version 9 license work with the new 9.3 release? No. So essentially, as Jim mentioned, we have this concept of subscription and perpetual. So if you purchase a perpetual license, then you have all the improvements from version 7 to version 9, and there were a lot of them. Then what we're doing now is for people who essentially have a subscription, a monthly annual subscription, they can access all the new material that's being developed, all the new features and functionality as it's developed. So rather than releasing version 10 in 3 years and then providing all that those new features and tools at that point, people who subscribe get immediate access when it's available. So we will have a 9.3, our third point release this year coming up. And now what you can do if you've already purchased version 9 perpetually, we have introduced a maintenance plan where you can essentially upgrade to a subscription level. And then what happens is, as long as you're paying the maintenance every month, then you essentially have access to the subscription features. If you decide you no longer need that access to those features in the point releases, and you no longer maintain the maintenance, then your license will revert back to the version 9 perpetual. So you always have that base code that you purchased with your perpetual license. As someone new to 3DEC who is planning to take the 3DEC introductory course in the ITASCA Software Academy to gain base knowledge, is that the only recommended course to take? Are there other available courses that reference 3DEC or of any additional use?
I think that's the best place to go. There's probably a few. Well, I mean, if you just look in the documentation, there's some getting started tutorials, which are pretty useful. I mean, I would do that first. There may be a couple of things on YouTube related to using 3DEC. I'm not 100% sure. But yeah, probably I would start with the getting started tutorials in the documentation and then look at the course on the Academy. Yeah, that would be the best way to go.
Okay. 2 more questions. Can 3DEC be run on a virtual machine using AVD, Android Virtual Device, or is it compatible with other virtual environments?
I don't know what that is, but yeah, I mean, for sure you can run it on a virtual machine. I mean, people do that all the time, so.
And then the second part of that question, to accelerate the analysis, was a GPU feature utilized in 3DEC to enhance computational efficiency and speed up the modeling process?
Short answer of that one is no. That's something we're working on right now, but it's not in there yet.
And then the last question, does implicit fluid flow fully saturate models?
Yeah, the implicit fluid flow is only right now for the joints, and the joints are always assumed to be 100% saturated. That's always been true in 3DEC. So.
Okay. And is the implicit fluid flow limited though to joints?
It's right now. It's just the joints. Yeah.
Yeah. Okay. Oh, and James Arth, our sales and marketing director, posted a 3DEC YouTube playlist link in the chat if you're interested. Cool. So there's all sorts of webinars and tutorials. So thank you, James, for posting that. Okay, I'm just going to switch over and share my screen. Okay, so I just wanted to put up this slide. Again, happy 3DEC Day. Thank you for everybody for joining us and for all the great questions. We have a few that we'll follow up on with you directly. To learn more about 3DEC or any of our other software, or to purchase online, please visit ITASCAsoftware.com. And if you are interested in trying out 3DEC or another code for 2 weeks, please shoot us an email at sales@itascasoftware.com. There's a QR code link there to that email. All right. Well, that concludes our presentation today, our webinar. Again, happy 3rd of December, 3DEC Day, and thank you all for joining us. Have a good day.